up. They will have 20 minutes for talking and 10 minutes for questions. And of course, we can just mute you if you go over time. So be prepared. And there's a special thing about this seminar because, or this webinar, we have a nice prize. And now I have to change my slide. So there's a first prize of €200 book voucher, which is kindly sponsored by Monster Sense. And there's also prizes for the second and third speaker. And you would say, well, who's then the experts that can tell what's the best speaker? Well, actually, we have right now something like 75 experts in the room. So you can participate after the last talk and help vote for the best speaker. So stay online and help us decide who's the best. And then you can, of course, choose one of these wonderful books. Or you can buy something completely different for your book voucher. So without further ado, I would like to proceed to the first speaker. And Pavel Malý already knows that he's going to go first. Maybe I would also like to say that he was nominated for this presentation by Tobias Brixner. And Paul is going to talk about pump probe spectroscopy with 6-way mixing and comparing coherence and population-based detection. And with that introduction, I would stop sharing and give the floor to Pavel.
And the talks, as usually, are recorded.
Understood. Okay, thanks a lot, Thomas, for the introduction and mostly for having me and hosting this great event. I'm enjoying very much every session. So today I'd like to talk about. I've been in Würzburg with Tobias Brixner. He's over here. I'd like to talk about what I've been doing together with these guys in the last 2-something years. And what we learned about was the difference if you do nonlinear spectroscopy and you detect it coherently and based on the population, like by fluorescence. So the guys I did with was Julian over here, Hans-Peter, and Stefan. This is the work we did. I will be presenting. Of course, we otherwise collaborate with many more people from around here and around. And the samples we got from our collaborators in organic chemistry from Christoph Lampert's group. Okay, so the kind of systems that we typically look at are open quantum systems. So what are these? Well, we have some kind of quantum system, and it's interacting in its bath like this. And then there's light, and the light can interact with our system. And then this leads to some dynamics of the system. And this is the thing that we want to study. We want to study the light-induced dynamics of the quantum systems. And now if the system interacts with this light field, it also responds in some kind of way. And then this response can be different things, but for the systems we study, which are molecular types of systems, this typically is a coherent polarization. So something like this, or a fluorescence. So the polarization can be calculated as a mean value of the transition dipole moment, for example, and this thing is dependent on the transitions between the states in the system. So then this polarization will be derived from the off-diagonal elements of the state of the system, therefore from coherences. So this is coherence-based response. Or the fluorescence, this is something which is proportional to the excited states of the system. So this is population-based response on the population of the excited state. And today I'd like to talk about what's the difference when you observe these two kind of observables, what you can learn about the dynamics of the system. So how we describe the dynamics? Well, we describe by perturbation theory. So we have this kind of equation and we solve it in the orders of perturbation with the electric interaction with the electric field like this. And then, for example, for the polarization, we can calculate the polarization in each order of the interaction with the electric fields. And then if one writes it directly, the expression from here, one gets that the polarization is a response of the system to this n interactions with the E fields. And the response is something like this. So there's a system in equilibrium, it's perturbed, it propagates, propagates, and so forth. And now for the fluorescence, you can do the same, of course. So you have the fluorescence of the nth perturbed order. And this nth order fluorescence is again response to the E fields. And you have again some kind of response function. And now if you compare these two response functions, you see that they are more or less the same. The difference is that here you have n times this transition dipole moment. And here you have also n times dipole moment operator, but here the last one ends with the commutator, and here's additional one from the polarization over here. Instead, here you have the projection of the populations and some evolution. And this is the difference which will then lead to the different physics you can observe when you observe these two kind of observables. So each dipole moment means a wave in the nonlinear wave mixing. So for example, for 4-wave mixing, you will have formally third order response in the coherent, a fourth in population. So always like one higher up in the population base. So this is a general thing. And now the beauty of this response function is that if you use short pulses, then they behave like delta functions in these integrals over here, and you're basically directly observing the response function. So you can basically directly follow the perturbation theory as it happens. So, you know, this kind of response and green functions and so on, it's just used in many areas of physics, right? But here we have the opportunity to really follow in time how the perturbation theory unveils. So this is very nice. So to introduce how this works, let's look at absorption. So linear absorption can be viewed as linear polarization. So you will have polarization as a linear response to the E field. The response looks like this. So the system equilibrium interacts, propagates, and then there's the polarization. And we can depict these by this kind of double-sided Feynman diagrams. So you have the system in equilibrium, interaction with E field, propagates, coherence, and then it produces the polarization. If you do the experiment, you can measure, for example, intensity before and after sample, and you get some absorption spectrum. In fluorescence, you get the second order fluorescence, again as a response, and then you see that the response is looks like this, and you can depict again by the diagram. So you have an interaction with the light field, coherence, another interaction, and they have the population which evolves somehow and produces the fluorescence. So then, if you integrate fluorescence in time and then Fourier transform everything, then you will get again some absorption spectrum. Difference will be only it will be multiplied by laser spectrum and the fluorescence quantum yield. So it's fluorescence excitation spectrum. Otherwise, it's the same. The nice thing is that you can do this, for example, on single molecules like Erling or Lukács-Kwiatkowski with Nick van Hulst and so on. And then essentially you're resolving the quantum jump in the absorption, because the system emitted over here because you detected the fluorescence and you were observing this coherent state over here. So what I'm saying, because I was recently reading some paper in Nature about still discussing about this nature of the quantum jumps in absorption and emission and so on. So I really think that one in this kind of experiment can actually resolve it. But okay, let's go to some more nonlinear time resolve stuff. So when you have absorption, there's only one step to transient absorption. To this end, you add you call the first pulse, which we just discussed, a probe, and you precede it by another pump pulse like this. And then the response is the third order in the coherent one and fourth order in the fluorescence one formally. And otherwise the structure is very much symmetrical or similar to each other. And then it works like this. You have the pump pulse, excites the system, then the excitation evolves in the population time, and then the probe pulse here induces this coherent polarization, which you detect. And in the population base, you have the two pulses for the probe. They create this population over here, between that oscillates, and then you can detect the fluorescence. And now the response pathways can be separated in three kinds. Here for the coherent ones, you have the bleach type, stimulated emission type, and excited state absorption type of pathways. And now for the fluorescence, for the population base, for example, you have the same three kinds of pathways, but an additional one because of the additional commutator in the response that we've already seen. And this kind of pathway has some consequences then on what you can actually see in the spectrum. So let's look, the sample which we used for most of the measurements I will show is this kind of dimers of squarines. They are made in the group by Christoph Lambert over here. They're very friendly and interesting people. So whenever you would be interested in kind of squarine molecules with a square in the middle, then you can contact them and they will be happy to collaborate. And these dimers we have is like squarine A, squarine B with a spacer between them. And the coupling is relatively weak. There's fast energy transfer, fast annihilation, and so on. You can consider them as like two coupled three-level systems. And they are bright in fluorescence, so they're good for this kind of experiments. And if you measure the fluorescence detected pump probe and coherent detected pump probe, this is what you get. So it's a dimer, so you have two peaks, so you have the upper peak and lower peak. Somewhere here, upper peak, lower peak, you can see. and they somehow evolve in time. And now I would like just to focus on one process, and this is the energy transfer between the two molecules. So this you see over here, for example, I mean, the theory and experiments sort of correspond to each other. So I will show on the theory slices because it's just the one on the top. And here you can see that this peak decreases and this peak sort of increases, and this is with the energy transfer. And here something similar happens. You can see in the traces on the top, but here the peak decreases completely, and here it decays a bit, but stays, you know, the stays bleached. So this is, I would like to explain, you know, why does the peak stay bleached when the energy is transferred away? So this is on first sight weird, no? So the process we're discussing is this. First, the excitations are in the ground state. Then the pump excites the first higher energy molecule to the excited state. And then in the waiting time, there's energy transfer to the lower state. And then the probe comes. So for the probe, for the coherent pump probe, this transition is not bleached anymore because it can normally absorb, right? So then this peak has to disappear. So this is fine. And in the language of the diagrams, this is expressed by this excited state absorption pathway eating this ground state bleach over here. So these two then cancel each other. So the meaning of the ESA pathway in the collective states over here is the recovery of the bleach over here. So, you know, this is something which always puzzled me a bit. Like if you draw just this bleach and say this is bleach, this thing does not involve the population time, right? This should stay there forever and ever. So there has to be some other pathway which recovers your bleach. And this is the formally ESA type of pathway. So, you know, these are just elements of perturbative expansion. You cannot call them like this is the bleach signal, right? These are just together, they correspond to the bleach and its recovery. Okay, all fine. How is it with the fluorescence? Well, you are in this state and what happens? Well, this is not the end of it. What happens is that these two excitons over there, they can like interact, and then this kind of process happens. So this goes down and this goes to some higher state, which then fast relaxes down here. This is called exton-exton annihilation. And what happened is that we had two excitations and we end up with only one. This decreases the fluorescence which we get. Mathematically, this is expressed by these two pathways canceling. So this ESA2 pathway cancels the ESA. Then the bleach does not recover and we stay bleached forever. We stay bleached because if the probe excites over here, it is annihilated. So that's why you still have this amplitude of the peak up there. And this is the meaning of the additional pathway over here, right? So this is, you know, there's one way to write the pathways and say this is the mathematics, but then to understand what's happening. Okay. Second big difference between the two is that there's, in normal pump probe, there's no signal before time zero, right? The reason is that if you reverse the Feynman diagrams, you have one interaction with the probe and you simply have a coherence which dies, right? Reverse induction decay. But in the fluorescence case, then you have two interactions with the probe and there's a population and this lives long. So that's why you have some signals before time zero. What do they mean? Well, if you write it down, you see that they are actually bleach type of signals. So you have like, this makes sense because the probe interacts with the system in the ground state. So then there's like bleach type of signals before time zero and bleach type and stimulated emission type of signal after time zero. You can see the stimulated emission like appearing over here. So this is very neat because you can use this. So what we did, we used this on this M-cherry protein. M-cherry protein is bright fluorescence protein, which is well known and so on. And then normally after, this is before time zero and after time zero, you see this stimulated emission appearing over here. And here is the bleach type. So if you take half of this bleach, subtract it over positive dynamics, you get exclusively, you know, like isolated this kind of just the stimulated emission part. So this is quite nice because you can stimulate emission in this way. So of course, like you can see differently, like for example, in 2D and so on, as shown in talks by Hovesian or by Jessica, but this is yet another way how to see this. Okay, I will finish with fluorescent pump probe. I mean, it's sort of not multi-dimensional experiment. I like it because it's a very fast, simple experiment. And it is something which I would like to apply in the microscope. I will try to do this after summer in Prague, Charles University. So it's in my head now, but now let's move on further to the 2D. So 2D spectroscopy, of course, I don't have to introduce. From transient absorption, it's very close. You just separate the interaction with these first two pulses, with making some time between them, and then you can get the spectral resolution also in the excitation axis. And then again, you have the same kind of response function, only now we have here omega tau, so you have excitation and detection. And then the parallel between the two techniques goes very deep. Here you have the phase matching, here you have phase cycling. They are very similar, and you can see that again, you have these three kinds of pathways in the coherent rotated 2D, and the same pathways plus additional ESA to the 2 exciton state in the fluorescence detected 2D. So what does this do? Well, and again, I would like to focus only on one feature, and this is the meaning of spectral correlations in this spectrum. To this sense, we have our dimers. This is our squarine dimers, and our collaborators, what they can do is they can make the dimers with shorter and shorter spacers over here. And shorter spacer means larger coupling. So then you can see somehow in absorption spectra that they split more and more, and it allows us to make this kind of axis over here when we have the increasing electronic coupling, and you have the spectra, 2D spectra for all these coupled dimers. So we have always experiment and theory. This is coherently detected, this is fluorescence detected 2D, and then with increasing coupling. And now there's of course many things going on, coherent oscillations, redistribution of oscillator strength, and so on. I will not talk about them. I will talk only about these cross peaks over here. Now, what is the meaning of these cross peaks, this correlation? Let's focus on this cross peak, for example, over here. So it starts at the lower energy, exciton 1, detects on the exciton 2. And you can understand these, you're looking at this picture. So the transition from the ground state to exciton 2, and then from exciton 1 to the 2 exciton state, this should be the same if the molecules are very weakly coupled, right? Because this is just in collective states, and otherwise it's, so these R2 should be the same, and this should be the same. And if they are different, then the oscillator strength is redistributed for increase the coupling, then this transition and this transition will be more and more different, and then there's some balance will be broken, and the balance is between this kind of pathways. So you look at the cross peak who corresponds, there will be these two pathways, and then when there's no coupling, they will be balanced and there will be no cross peak. But if there is this delocalization of excitons, you redistribute oscillator strength, and then the cross peak appears. So then this cross peak will reflect this delocalization of the excitation. Now in the fluorescence 2D, you have again these two pathways together, and then they are canceling if you have efficient annihilation as we have in these dimers. So then you are always left with this clean bleach signal at the presence of the cross peak. So, there is, you can look at it as the advantage, there's a clean bleach, great, you can see it from the beginning, but of course it's the annihilation which is correlating the two transitions at the two molecules. So you can then say what are these cross peak signatures of, how they change with electronic coupling. So you can see that these are in the squares are in the coherent detected 2D, they increase with the coupling, the cross peaks, and in the fluorescence one, they just decrease a little bit. In theory, it's the same. Actually, it's the same as in our previous theory, which we did with Tomáš Mančal back in Prague. So you can show that the cross peaks are sensitive to the coupling between the molecules, and the cross peaks in the fluorescence 2D actually not so much. They just decrease a bit. And this is what we see also in the experiment. So that's nice. And of course, you can show theoretically that if you are switching off annihilation going down here, then the cross peaks will also disappear and you will recover sort of normal 2D theoretically, right? So we were interested in this cross peak so much. Oh yeah, of course, you can interpret these things also as a two particle observables. Like you're thinking about emitting two photons, from the two, and then annihilation isn't decreasing this two particle observable. So this recommended in this paper. You're interested in this cross peak so much that we looked at the mixture of independent molecules, squarine A and squarine B. And then of course there should be no cross peaks. So we are happy that there are no cross peaks. This is in solution, so you don't expect any interaction between these. Okay. And now we also measured, this absorptive spectrum. And if you measure double quantum or non-rephasing spectra, you get this kind of shapes, independent molecules, and you get this kind of cross peaks over here. And they're like what, right? Can there be coherence between the molecules? This would be if you draw the diagrams for the double quantum diagram, right? This is here the double quantum coherence, and here is this coherence between the two molecules. But then do the theory, you calculate one, another one, you add them, and again, there are these cross peaks, and they are really just from these extended line shapes. When they cross, they just produce these cross peaks. The interesting thing is that, of course, one would be very tempted to use the time zero spectra in the fluorescence detected case because there's no coherent artifact, but there is still the pulse overlap. And then the double quantum and non-rephasing pathways both contribute in the pulse overlap. Then you have the non-rephasing one contributing there, and it can produce this kind of cross peaks even for independent molecules. So this was nice verification for us. So there's a lot of discussion about similar things. So, you can get cross peaks by other ways. For example, by coincidence detection, as was shown by Shalmukamel or so. And yeah, there's of course a lot of great literature also on these effects of the pulse overlap and so on. So I recommend for further reading. Okay, I will skip this. Now, very briefly, one can also go to higher orders of perturbation theory. in the 2D. So this is our 2D spectrum at a single frequency, single omega frequency, and one can extend, scan a much more fine scan in tau, and get a 2 omega signal over here. And this then would be 5th order response function and so on. So we did that, and again compare the fluorescence detection and the coherence detection. The spectra look something like this. And they have interesting features. You see that this is now focus on this right block over here. So then you can see that there's this kind of like, you know, 2 peaks in the coherent one, and there's this kind of funny weird structure of the, let's say, 2 states along the detection axis, but like some distorted state along the excitation axis for the fluorescence detection, and one can sort of reproduce by theory. And again, you can write a lot of the diagrams. You have contributions from bleach, from bi-exciton states, from annihilation, from single exciton dynamics. And it turns out that, again, you have these pairs of pathways which cancel each other. And if you are interested in these higher orders, we are developing, then you can, for example, look in our publication. But, there's enough of this pathway canceling all the time, right? There's a situation when this kind of SA2 pathway actually is not just canceling another SA. And the situation is this one I want to show you. This is the last thing I want to show you. Is a molecule, for example, like azulene. This one can produce signals only from its S2 state. And the point is that you excite it by 2 photons to S2, and then it fluoresces, or you can ionize it. But it does not fluoresce from S1. It's hard, when you set the energies right, you cannot ionize it from S1. So then you have only this kind of pathway for ionization, and then you measure the mass spectrum, or this kind of pathway, and then you measure the fluorescence. And then the other pathways this time don't contribute. So this time you measure exclusively this SA2 pathway only. So then this allows you to do this kind of things. So we measured in liquid by fluorescence detection, and in gas phase in a supersonic jet by photoions detection. And then along this axis, you have the excitation from S0 to S1, and here from S1 to S2. So you're like climbing up this ladder all the time, up, never down, never any ground state contributions. Any dynamics that you see has to be purely in S1, for example, and so on. So this is very interesting. Another interesting thing is that it essentially means that you're taking away the solvent path. So we started and we end with the molecule or system which is interacting with its bath, this time the solvent. Then molecule responds to light, and you have the 2D spectrum. You can, for example, look at line widths, how much interacts, homogeneous line width, and so on. Then you can remove the bath, and again, look at the response of the system in a supersonic jet, and then you get the line widths over there, and they're narrower, and the dynamics is different, and so on. So this is pretty cool because you can study the system and say something about the importance of the intramolecular vibrations, and so on. So this is the kind of things that you can do with this SA2 pathway. So it not always just cancels the other ones. Okay, and with this thing, I would like to summarize. So you observe the same order of wave mixing, formally 1 order higher repetition theory in the population with observables, as we have seen. So like from the 3rd order coherent response, you have 4th order population based and so on. There's this additional response pathway due to the extra interaction, which is formally a SA type pathway. But its meaning is, of course, derived from the yield of the multiply excited states that we've seen the 2 different examples. One is yield 1 of the annihilation, one is yield 2 with, absolutely all the signals coming from this multiply excited state. If there's a lot of annihilation, then you have bleach type signals. And then the implication for the pump probe and 2D is that you have these peaks even after recovery to ground state. Cross peaks are arising from correlation by annihilation. And if you have fast recombination, then the SA disappears. And if you have the signal only after this high excitation, then you have this single pathway 2D, which we think is pretty cool. And we're now working on what we can learn from that. And with this, I'd like to end with a picture of our group skiing with our friends. This is 1 year ago when it was still possible, and I hope this will be possible soon again, and to meet sometime in person. Thank you.
Thank you very much. Questions for Pavel? Aaron?
Aaron, please go ahead. You can switch on your mic and ask your question.
Yes. Hi. Very nice talk. I was curious, can you go back to the exciton annihilation with the dimer, that particular slide? The question was that it seems that you didn't take into account the local double exciton states because the number of double
Okay.
exciton states
Yeah,
will
yeah,
be
yeah,
key, right?
yeah.
In
In
And
the
it is
pump probe,
known that the local ones are more prone to exciton annihilation. So my question is towards that. So this one,
you think in
yeah.
this picture or in the
In this picture, we can discuss in this picture. I think it's the same
So
substance.
local. So yeah, I'm not sure you mean, what do you mean by local to exciton?
So I
You
mean
the
the
higher
twice
excited
the
state of the molecules, you mean?
yeah, twice E2 and twice E1. There should be three states.
So yes, yes. So this indeed would for sure contribute and so on. But in these molecules, the structure is such that this, like, there's not actually a nice ladder of states, but the higher excited state is lying lower than this 2 exciton state, and then it's outside of our laser spectrum. So we don't directly probe them. You
But
see these
is
states
the
because
conclusion is your conclusion then that these delocalized 2 exciton states, they are also prone to exciton annihilation? Is that the conclusion?
Oh, so we don't say anything about the localization of the 2 exciton state. Formally, an exciton model, if you have a 2 exciton state, then it's always localized because it has nowhere to delocalize in this sense. Because, you know, if you like delocalizing Hamiltonian, this guy doesn't interact with anybody, right? So it could delocalize to the higher states over here and over here, but this is because of this big energy gap, this is actually weak. So I was talking about localization of these single excitonic states, and then there's this annihilation.
I mean, because I dealt with a light harvesting complex too, and there, if you have 105 2 exciton states, and there you will see that they can actually delocalize in a sense if you have between the mu1 2 that you wrote. If you have interaction between them, they can, I mean, in the Hamiltonian, there are possibilities, but you have to write higher order terms. That's what
Absolutely. Then the multi-exciton states indeed can be and will be delocalized around. And then, then you can talk about the annihilation of this kind of states. I mean, annihilation is always the kind of process I was depicting, right? So you have to go through some higher excited state on like one molecule. This will be localized through and so on. This will happen. And of course, in this case, you expect very efficient annihilation.
And one more question, maybe it's a bit stupid one. So in the single exciton manifold to the ground, is there any non-radiative pathways? And if there is, what would be the time scale?
Of course, yeah. So these pathways have to be there because otherwise you would not see the signal, the fluorescence signal. So, but they are here. We are lucky in this system because they are there's complete timescale separation, though. So here, this is on about 3 nanoseconds. This lifetime of the excited state. And 75% is the radiative rate. So this gives some is the quantum yield. So this gives somehow the radiative rate out of this. So this is nanoseconds. So everything happens, with these pulses, annihilation, and so on. Then it sits in the excited state quasi-stationary equilibrium and slowly radiates.
Thanks.
Okay, Jürgen, could you please just unmute and ask your question?
Sure, thanks. Sorry, my voice is a bit, I've got a cold. Anyways, hi, Pavel, great talk.
Hey,
on your, I especially liked the easy part in the beginning, which I'm still able to follow, with the incoherent pump probe.
Incoherent pump probe,
yeah. So that was very clear that, you have a bleach signal with 4 times 0, and then you can beautifully subtract that to get just the stimulated emission out and so on.
Oh, yes.
Now I still have a problem with non-decaying ground state bleach pathways, right?
Okay.
So essentially, what you're saying is in your incoherent pump probe, you should not see the ground state bleach pathway decay as it should in the coherent, right? However, when I look at the signals, both in theory, I'm not sure, but in experiment, it definitely decays. So
okay, let's see. Let's check it out.
The time we are observing here in the incoherent.
Okay, absolutely. So it should not, So you can see over here, right, this is measured here, and So then this pathway, I mean, so there's the contributions to the decay of the upper peak, right? Would be like the short time scale, which is the energy transfer, and there's still the stimulated emission part. So you should see first stimulated emission from the top and then from the bottom one. This is still there, this pathway. This still contributes.
Okay, but that disappears.
I mean, so this is like a little bit, and you can see it. You can see over here in this rise of this lower peak and this decay of this one, and then it stays, and then it decays with the lifetime simply of the excitation of the excited state. So when I mean, all signals in this incoherent pump probe, they should decay with the lifetime of the excited state. So then it has to decay afterwards.
Okay, and that also applies to the bleach pathway, huh?
Yes, yes. Precisely. Yeah. So this bleach is then this has to be filled then. Yeah.
Vivek, please go ahead with your question. Vivek, I just promoted you to the panelist, so you can unmute and ask your question.
Can you hear me now?
Yes.
Hi, Pavel, great talk. Actually, I had a quick clarification about, so what exactly do we mean when we say correlation by annihilation? And I'm asking it in the context of, let us assume that we are thinking about a system where, fluorescence detected system, but let's say there is no annihilation. Well, in that case, we know that, for a weakly coupled case, the cross peaks vanish, but they do vanish because, there is a contribution from ground state bleach, which cancels out with the, the doubly strong excited state signal. So overall, I'm trying to understand the origin of these ground state bleach cross peaks, and like, how do we know that these cross peaks are really there because of a shared ground state, or are they simply there because of correlation by annihilation? Like, is there a simple way to differentiate these?
Okay. So where to start? This is indeed like the good direction of questions. I mean, we were thinking about this, took some time. So what I mean by correlation by annihilation is that I have independent molecules, and they would be, let's say, they would be, like no. Of course, you can collectively write them with some collective ground state, but it's just mathematics, so they will be completely independent. Now, like, they emit, right, and whatever, produce some 2D signals, and these should be completely like independent, right? So 2D plus of the signals should be just composite of the two 2Ds. Sure. There should be no cross peak, right? And now you can come up with processes, and then if you write this in the pathways, you will have that you have to have this kind of pathways contributing, right? And this kind of thing formally, mathematically, right? And mathematically, this is just about a probability. So what you're doing is measuring, and you're detecting probability of getting a photon from this system and this system. And then mathematically, you get the probability of getting photon from this and from this and from both. And only when you sum this, you will get it. And now, if you come up with a process which is somehow changing this, for example, changing the probability that whenever to get a photons from both, right? Like annihilation, which whenever you will have two excitations there, you don't get two photons out. Then this will like correlate. This will correlate the signals from the measurements, and this will lead to the cross peaks. So this has been nicely described in this paper by Tomáš and Oliver and Tonu. Then when you take the multi-particle observables, you will get like this. So this is what I mean. There's different ways how to get cross peaks. Like you can, for example, have a nonlinear detector, and then this guy is mixing your signals together, and you can also getting and so on. So so this is what I meant. Yeah.
I mean, I guess maybe we'll take this discussion somewhere. But I was trying to understand. Are the ground state cross peaks really there, or they? How do I differentiate between a situation when they're really there, or when they're there just because it's simply an artifact of how we are thinking about, two independent systems and highlighting. Then we still give them a shared ground state, and that's why we think about these GSPs. In that case, we cannot think of them independently. I understand that, but
just as an for like a longer discussion, because I never I would like to go at some point deeper into this notion of the shared ground state, because what you want to say that you like bleach one of them and this bleaches the other one because it's missing the electron in the ground state, right? So this kind of thing you're thinking, and then in normal exciton model this doesn't happen, right? So it's okay.
Thank you.
Sure.
Okay, I understand that Eric has a question. Eric, go ahead, please.
Thank you. Pavel, great job, enjoyable to watch. You've done a lot here. I was a little curious. So near the end, you were talking about you did a single quantum scan, but we're looking at a double frequency of where your single quantum. I'm a little confused about where that signal is coming from. In terms of what kind of measurement are you doing here, and why does that exist?
Absolutely, there was I was completely no time, and I did not intend to talk about it. So sorry for the briefness. The point is that you measure like a normal 2D. So you scan. So we measure in pump probe geometry, for example. This doesn't really matter. So you scan your two pump pulses over each other, and now then you acquire the interferogram. And if you have like two level system, then this will oscillate at the frequency of the transition, right? And now if you will have like two interactions with the first pulse, this will create a superposition of the ground state and some doubly excited state. In the dimer, which we have here, we have only one doubly excited state of both of the molecules excited. And this is the coherence, optical coherence then, which propagates in the time between the two pulses. And then the second pulse also has two interactions. And then it can lead to all these kind of pathways. So, I mean, this is very small, but this is the thing I'm talking about. So here, for example, yeah, let's see.
So this is a typical double quantum, but you use a single pulse that just acts twice.
Wait, yeah. So the two interactions.
This is a double quantum measurement, and then, but you're really scanning an optical frequency here. So you just have an optical interferometer.
Yes.
You're not doing any sort of frequency.
Yes. I mean, you can do, right? We have a pulse shaper. So what you can do, you can go to rotating frame and you can move them closer together, for example, and so on. You can like down rotate the frequency. So you don't have to, this thing was scanned for real, like brutally with the small steps to get all the.
That's what I was wondering if you were scanning. Okay.
Yeah. So in some measurements we do, yeah. So then you start rotating and this guy gets together closer to this one. You have to take care they don't overlap. If you don't want to phase cycle, you can also phase cycle. Then you don't have to. Then they overlap and you have everything around your zero frequency, and then you can distinguish by phases and so on. Yeah. But this was scanned brutally direct optical. Yeah.
Okay. And so then now in the previous slides, when you were talking about doing double quantum, but you had single frequencies. Was that what were those?
This is the first pulse and the second pulse, and then there's the double quantum coherence not in the.
But you're not scanning that.
But in the second interval. Beg pardon?
Are you scanning that, or you're not scanning that?
Yeah, this.
Because all the frequencies here are single frequencies.
Yes. So this is the old school double quantum, like is done, I don't know, by Jürgen and so on. When you do like the first pulse, scan this tau, and then you have single quantum frequency. Second interaction with the second pulse, you get this two quantum coherence, and this would evolve in the population time. Right. So this you scan in your second time. This is the thing which we typically scan with delay stage in the coherent, and here everything with the shaper, and then the third pulse. So this differs because this is lower order of nonlinearity. So in this thing you get this information about this double quantum state, but only in the coherence. In the fifth order. And the higher orders, you get it in the population. So then you get the effects like annihilation. Here not. Here you get just this line shape of this double quantum coherence.
Okay, thank you, Pavel.
Welcome.
Okay, I think we should thank Pavel for his presentation and all the nice questions. And then